Hello everyone, welcome to your first physics instructional video for this year. And today I'm going to be going over the review problems for the open-ended questions that I gave you on Friday. So I'm just going to jump right in. I'm going to tell you as much as I can while not being redundant. So I'm probably not going to go through all the solutions for this one, just sort of the ones that might not be obvious. So, your friend has a good business idea and he wants to make physics flashcards and sell them to other people. You want in on all the physics cash, so he asks you to make flashcards that use different representations to show motion. You need to make flashcards representing the following types of motion. Each card should show a word description, a complete motion diagram, position versus time graph, velocity versus time graph, and an example equation for something moving that way. So, most of these are pretty straightforward. I'm not going to go through all of them because we've done several examples of each. You can also look at the instructions on the SchoolFusion site, or the solution on the SchoolFusion site, in the solution file that I posted. The answers there are pretty straightforward. The only one I guess I really want to talk about is the turning around one. That is the only one that is kind of complicated. So, first of all, the motion diagram for something turning around. Obviously, this can be going in either the negative direction or the positive direction. Okay, so you can start going in the positive direction, turning around going in the negative direction, or vice versa. And what this is going to look like is a motion diagram with something going slower, then reaching sort of the stopping point, and then picking up its velocity in the opposite direction. Whatever, it's not pretty, but it is what it is. And this would give us a delta V arrow going this way. Remember, the delta V points either in the direction of the bigger arrows, or you can see that up here, if I go from this V1 to this V2, the arrows get squished as they keep going, and then here they get stretched out as they go this way. Similarly, for the opposite direction, we could have objects starting out going this way, getting smaller and smaller, and then reaching again the end, and then going the opposite direction, getting bigger and bigger. And this would have a delta V going this way. These are supposed to be the big fat arrows, don't forget. And again, because of the same reason, if you go from V1 to V2 here, this arrow V1 is getting squished to become V2, whereas this arrow is getting stretched to become this one. So this would be something moving at first in the negative direction and turning around and then going in the positive direction. This one's something going in the positive direction, turning around and going in the negative direction. You may recognize this as an object. This is the same motion as an object that is thrown into the air. And you'll notice that the delta V for both sides is going to be in the same direction. That's what causes it to turn around in the first place. Now, for a position versus time graph, it's actually fairly simple, because all you need is to show either one way or the other that it is moving first in the positive direction and then in the negative direction, or vice versa. Okay, I just wanted to move the axis here to show you that it doesn't matter where it is. So for the positive direction, moving in the positive direction first, that would be this one, and then back in the negative direction, which we will make red just for fun, would look something like this. Okay, notice this is moving in the positive direction, it turns around and comes back in the negative direction. This part here shouldn't be so wide, but notice that it does stop at the top here, V equals 0, before it turns back around. And then for something moving in the negative direction first, turning around moving in the positive direction, which will make green, would be something like this. Okay, so again, starts moving in the negative direction, stops here, V equals 0, turns back around and starts moving in the positive direction. For a velocity versus time graph, we are moving with a constant acceleration the whole time, so we're not going to have to worry about a curve. We're going to just have straight lines, because the slope of a velocity versus time graph is the acceleration. For the object moving in the positive direction and then turning around the negative direction, we'll start with some non-zero velocity, moving in the positive direction, being in the positive quadrant, and going down towards the negative quadrant, something like that. Alright, so here it is moving in the positive direction because it's in the positive quadrant, but slowing down and going to 0. and then it continues with the same acceleration, the same slope in the negative direction, because now it's in the negative quadrant, moving again with the constant acceleration. And then for something moving in the negative direction, turning around and moving in the positive direction, you have something like that, where you have it moving in the positive direction, in the negative direction first, excuse me, stopping, and then turning around and moving in the positive direction. And so for the equation for this, you can see on the handout, on the solution sheet, any equation where you have it starting, essentially starting, if you have it start at 0 and then ending back at 0, it'll count as if it was moving, the position versus time equation would have it moving as if it was starting at the 0 point, went up and then back down and ended at the 0 point. But again, look at the solution manual for that, the solution guide for that, just to be sure. All right, without further ado, let's move on. All right, an engineer is trying to develop a new type of bulletproof cloth that would be used in clothing to protect anybody from police officers to civilians. From his tests and research, she, I guess whoever wrote this mixed up the gender halfway through there, she knows that a 5mm thick sample of material can slow down the bullet at a rate of 9,600 meters per second squared. If the bullet travels 400 meters per second, is this material thick enough to make safe bulletproof clothing? Note that 1 meter per second is about 2.24 miles per hour. So this is going to be very fast as far as bullets go. So the first thing we want to do is draw a picture, right? That is the first step for any kinematics problem. So here is a sample of our cloth. We know that the distance here is going to be 5mm, which is equal to 0.005 meters. Remember, we need things in meters because we're doing everything in meters per second. And we know that our initial velocity, so our bullet, has an initial velocity of 400 meters per second. And we know that the acceleration in this case, if we make this negative and this positive, our velocity is going to be positive, our acceleration is going to be negative 9,600 meters per second squared. Okay, so this is a complete diagram. Okay, if you want to draw a motion diagram, you can just show that this is going to be moving in the positive direction with a very big velocity and slowing down. We're not quite sure if it's going to be able to slow down in this distance, but we'll find out with our delta v, of course, being this way. All right, negative, positive. Okay, so we have our given values are, we can say that we know x initial, right? Because x initial, if we know the total displacement is going to be 0.005, excuse me, then we can say our x initial is 0 and our x final is equal to 0.005 meters. Or we can just say that delta x is equal to 0.005 meters, depending on what equation we want to use. We know that our v initial is 400 meters per second. We know that our acceleration is negative 9,600 meters per second squared. And that's all we know. We're hoping that v final is going to be 0, but we don't know that necessarily. So we don't really want to use that. We don't know how much time it's going to take to get through. Notice time is not given here. So my first instinct, as soon as you see that time is something that is not given, would be to use the timeless equation. Okay, which, if you recall, looking at your equation sheet, is v final squared is equal to v initial squared plus 2a delta x. So we know v initial from here, and we know acceleration from here, and we know delta x from here. So one way we can solve this is we can plug in all our values into this equation and find out what our final velocity is. If our final velocity is either negative or not 0, or 0 rather, then we can assume that it manages to stop part of the way through. I think you can tell basically though that it's not going to be the case. So plugging in, we get v final is equal to the square root of v initial squared plus 2a delta x, which is the square root I'm going to fast forward ahead here to filling in the solution, because you don't need to hear me talk it all the way through. Alright, that's what we get when we plug that all in. Notice I wrote in the units, very important. And when we solve this, if you want to plug that into your calculator right now, you can go ahead, but you're going to get 399.87 meters per second. A far cry from the required 0 meters per second we would need for this thing to actually stop the bullet and for us not to get shot. So that's a definitive does not work. Alright, so that's that. Moving on. Problem 3. The Hamburglar is running away from Ronald, having stolen one too many Big Macs. He's got a 240 meter lead start on Ronald and is running at a pace of 4 meters per second. These are important. We'll need that. Can't run that fast after you eat that many burgers. Ronald is out on the hunt and is seeking compensation in blood. Mr. McDonald is chasing after the Hamburglar at a breakneck pace of 10 meters per second. Draw a picture that shows the situation, create a position versus time graph for both of them, and then create their corresponding mathematical expressions. Find out when and where Ronald takes his pound of flesh from the Hamburglar. So I'm going to refer you back to the picture in the solutions handout because it's a good picture. I can't draw that well on here. And as for the motion diagram, or as for the graph, excuse me, I can just draw that out quickly. So if you'll recall, we know that the Hamburglar is moving with a velocity of 4 meters per second. We'll make the Hamburglar, let's make the Hamburglar in blue. And we know that Ronald, who is obviously red, is going to be moving at 10 meters per second. This is a constant velocity here, right? So our position versus time graph for both is going to be constant. Let's say that, based on the picture, we say that Ronald starts at 0, so we'll start him at the axis, at the origin, and he is moving faster than the Hamburglar, so we have to make sure that his slope is obviously bigger than the Hamburglar. And we can show a little indicator here that this slope is actually 10 meters per second, with his x initial is equal to 0. Okay, and then we can do the same thing for the Hamburglar. He started slightly ahead, 240 meters specifically. It's quite a significant head start, but his slope is significantly less than Ronald, who had a 10 meter per second pace. His is only 4 meters per second, and he started at 240 meters. Okay, this is all important information you need on your position versus time graph, okay? So going from here, this was the Hamburglar. We can label these. This was Ronald. So now, going from here, we can set up the equations for the two of these. For Ronald, we have position Ronald as a function of time. Sorry for that weird R. This is going to be his initial position. Remember that position as a function of time is equal to, so remember that position as a function of time is equal to 1/2 a t squared plus v initial t plus x initial. Now for this problem, acceleration, these are constant velocities, acceleration is 0 for both, so we can ignore this part, we really just need this. So for Ronald, we have a velocity of 10 meters per second. Notice these are both positive. We have them both running in the positive direction according to the picture. So initial velocity is 10 meters per second times t. And notice a function of time means you do not plug in time, okay? In any other math class, if you were to write a function in terms of x, you would not plug in the value of x when writing out your function, 2x plus 9, right? You do not plug in x. Same thing here. If you're asked for a function of time, you do not plug in time here. All right, this is a mistake that far too many people are making for me to be comfortable with it. All right, anyway, back to the story. So 10 meters per second plus our initial position, which for Ronald is 0. Now for the Hamburglar, as a function of time, we've got his velocity, which is 4 meters per second, also positive. They're both running in the same direction. t plus his initial position, which is 240 meters. All right, so we drew the picture, we created position versus time graphs, and their corresponding mathematical expressions based on this. And now we have to find out where and when Ronald takes his pound of flesh from the hamburger, when do they collide. So we're looking for essentially this time right here and this position from here. So we're looking for this. What time is this and what position is this? If you can tell from your graph, that's great. We obviously can't tell from this graph because it's not accurate. So the best way to handle this, since we don't know what this time is we can decide that whatever this time is, their position is going to be the same here. So what we'll do is we'll take these two equations, and we know that whatever the time is, these two things are going to be equal. So we can set the two equations equal to each other. So we've got 10 meters per second times t is equal to 4 meters per second times t plus the initial 240 meters. So doing some algebra, subtract 4 from both sides here, we've got 6 meters per second. T is equal to 240. Dividing out 6 from both sides, you end up with t is equal to 40 seconds. So that's how long it takes for them to collide. And then taking the t and plunging it back into whichever one of these equations we want, I'm going to go with this one because it's easier. We get that the position at t equals 40 seconds is going to be equal to 10 meters per second times 40 seconds, which is going to be 400 meters. So their position is going to be the same. They're going to collide, or Ronald's going to catch up with him at 40 meters after 40 seconds. Oh, sorry, 400 meters, 400 meters after 40 seconds. All right, moving on down. Problem 4, describe them. So this is a hello, Mr. Graph. This is a velocity versus time graph, right? Describe the motion of the object in words. How far did the object move from 0 to 12 seconds? If the object's initial position is 70 meters, where is it at 22 seconds? And what is the object's acceleration from 22 seconds to 26 seconds? So, I'm not going to write this out, but I'm going to say it because I can. The object starts with an initial velocity. We don't know what the initial position is. We do know that it starts with an initial velocity of positive 2 meters per second. Remember that if it is in the positive quadrant, it has a positive velocity. I'm just going to write positive here and negative here. So anything below the axis is going to have a negative velocity. Anything above the axis is going to have a positive velocity. So the object starts with a constant velocity of 2 meters per second. Constant 2 meters per second, positive, obviously. At which point, after, what's that, about 8 seconds, he starts slowing down, or she, or it, whatever it is, starts slowing down because it goes from 2 meters per second starting to approach 0, right? At 12 seconds, the object stops and then promptly turns around and starts speeding up in the negative direction. So this, again, is slowing down in the positive direction, and this here is speeding up in the negative direction. All right, at some acceleration, which I will determine later. So at about 20 seconds, it looks like, the object stops speeding up and maintains a velocity of negative 4 meters per second for roughly 2 seconds, it seems. At which point, the object starts slowing down again. Now again, going from negative 4 back towards 0. So it's starting to slow down. And then at 26 seconds, the object reaches 0 and stays there, so it comes to a stop at 26 seconds. Okay? How far did the object move from 0 to 12 seconds? So that's from here to here. Now you'll recall, it's asking how far did the object move. So essentially it's asking for delta x, which for a velocity versus time graph, and this is something that I would write down on your equation sheet somewhere, from a velocity versus time graph, the displacement is the area between the graph and the x-axis here. Okay, so this area, whatever it is going to be our displacement. The easiest thing to do here would be to split up the two shapes, so you've got one triangle and one rectangle, and adding the two displacements together. So for the rectangle, our area is going to be 2, it's 2 high, times 8, right? Yeah. So we're going to have 2 meters per second times 8 seconds plus the area of our triangle here, 2 meters per second, well, 1/2 times 2 meters per second for the height times the 4 seconds from 8 to 12 seconds times 4 seconds. And so multiplying these two together, you've got 2 meters per second times 8 seconds. Notice the seconds cancel out, so you're left with 16 meters here. Plus, that's a 16, plus 1/2 times 2 times 4, which is going to be 4 meters. Adding these two together, you've got 20 meters. That's your displacement. That's for part B. For part C, if the object's initial position is 70 meters, where is it at 22 seconds? So now we're going to do the same thing, but this time we're going to take the displacement all the way up to 22 seconds, which is right here. So we already know our displacement from here, so we don't have to calculate that again, but we do have to find the displacement here. So we can use the same method that we used last time, where we take the area of the two shapes that we've got here, but notice this time our velocity is not positive, our velocity is negative. So our area for the two parts, so we'll call this delta x1, or delta x from 0 to 12. Then our delta x from 12 until 22 is going to be the area of the triangle here, which is going to be 1/2 times the height, which is -4 meters per second, times the time, which is from 12 to 20 seconds, so that's going to be 8 seconds. Then the second half, which is going to be just the rectangle, so our velocity again, or our height again, is -4 meters per second. And our time is just 2 seconds. So adding these up, multiplying them out, we get 1/2 times -4 times 8, which is going to be -16 meters, plus -4 times -2, which is -8 meters, which is going to give us -24 meters. So that is our displacement from 12 to 22 seconds. So to find the total displacement, or our final position where it is, we have to add everything together. So we have our x initial plus our delta x from 0 to 12, plus our delta x from 12 to 22, which is going to be our initial position, which is 70 meters, plus our first displacement, which is 20, plus our final one, which is -24, so this is -24, which is going to give us a final position of 66 meters. So 70 plus 20, or 20 minus 24, which is -4, plus 70, which is 66. Beautiful. What is the object's acceleration from 22 seconds to 26 seconds? So from here to here, finding the acceleration, which is oddly simple, is just finding, if you'll recall, the slope of this graph. The slope of this graph of the line for a velocity versus time graph gives you the acceleration, right? So acceleration, if you'll recall, is delta v over delta t. You can also just calculate the slope here. So our delta v is going to be v final, which is 0, minus v initial, which is -4, over 4 seconds. So f 26 minus 22 So you've got 4 over 4, which is 1 meter per second squared. Notice it is positive 1 meter per second squared. That is our acceleration there. All right, moving on. Last one. This one's the doozy. So this is a projectile motion problem. This is probably one of the harder ones that we're going to do. So a fighter jet is trying to hit a test target with a bomb. The bomb is released at 90 meters per second, 25 degrees below the horizontal. If the bomb needs to hit the target, which is 900 meters away, how high must the plane be from the ground when it releases the bomb? What assumptions are you making? So I'm going to actually take the picture and put it here so that I can reference it. There it is, and you will definitively recognize this as not my handiwork. This is someone else's. I'm sure you can guess who. So, how do we approach this problem? Well, we know that we are going to try to hit this target, which is 900 meters in the x direction, right? So we know how much, and we don't know how high we are. We know, well, let's. So how do we approach this problem? The first thing I would do is start assembling your information in the x and y direction. What do you know for x and what do you know for y? We know that in the x direction, x initial, according to the above here, is 0 meters. We know that x final is equal to 900 meters. We can find our velocity in the x direction. We can find that, which we will do in a sec. And we know that acceleration, at least we are assuming, acceleration in the x direction is 0. We assume that the acceleration in the x direction is 0. Notice you're supposed to note what assumptions you're making. In the y direction, we know that we don't know our initial y. That is a question mark. We do know our velocity initial in the y direction. We can find that from this part again. And we know that the acceleration in the y direction is equal to g, which in this case is a negative 9.8 meters per second squared. Right. And that's pretty much all we know here. Oh, I guess we know that y final is equal to 0. We're assuming it hits the ground. So, and obviously throughout we don't know what time is. But we will need that. That is something we will need. So, the first thing we need to do is be able to find our velocities. Once we have our velocity, for the x direction, we can then find how long it's going to take to hit this target going this way. And then we can set our y naught so that the jet is high up enough above the ground so that that's how long it takes for it to fall the distance that it started. Okay, so let's first deal with the triangle. So we have our triangle here. This is v naught, which is equal to 90 meters per second. And we have our angle here, which is 25 degrees. So we are looking for v naught x and v naught y. You can use your SOHCAHTOA knowledge to find that if we want to find, let's say, v naught x. So v naught x is on the adjacent side here to the angle. So we're going to use cosine, to find our v naught x. So cosine theta is equal to adjacent over hypotenuse. It's going to be v naught x over v naught. Solving for v naught x, you've got v naught x is equal to v naught cosine theta. So v naught x is going to be equal to 90 meters per second times cosine of 25. This turns out to be 81.56 meters per second. And that is v naught x. V naught y is going to follow the same steps, only instead of cosine, it's on the sine side. So the solution ends up being the same, or the method ends up being the same. So v naught y is going to be v naught sine of 25 degrees, or of theta. which in this case is 90 meters per second, times sine of 25, which is equal to negative 38.03 meters per second. Notice it is negative, not because that is the cosine of 25 or whatever, but because it is pointing down, right? Up is positive, down is negative, so that is very important. You got to make sure to include that. All right, now that we know this information, let's start solving. So for the x direction, we know that it is 900 meters away. It is moving with a velocity in the x direction of 81.56 meters per second, and the acceleration is 0. So using position as a function of time, we find that x of t is equal to x initial plus v initial t plus 1/2 a t squared, ax t squared specifically. We assumed that a is 0, so that goes away. So we're just left with 0, well 900 meters is equal to 0 plus our v naught in the x direction, which is 81.56 meters per second, times t. Dividing both sides by 81, you get that t is equal to 11.03 seconds. Now, taking this information and plugging it into the y position as a function of time equation, which is y naught, which is y initial plus v initial yt plus 1/2 a yt squared. Plugging in here, we don't know what y naught is. We know that yt is equal to 0, is equal to y naught plus, got negative 38.03 meters per second, times t, which is now 11.03, shoot, I'm going to go a little long, plus 1/2 negative 9.8 meters per second squared, times 11.03 squared. There you go, squeeze it in there. Solving for y naught, so you essentially add this to this side. You end up with y initial is equal to 1015.6 meters. So that is the height that you need to be at so that it hits the target. Obviously, again, we say that the assumptions are that the acceleration in the x direction is 0, the velocity in the x direction is constant that we found here. Obviously, if the acceleration is 0. And here we assume that the acceleration is actually negative 9.8 meters per second squared. That is actually an assumption that is not necessarily a given for reasons that we will discuss next season. But with that, I will leave you, and good luck on the test. If you have any questions, obviously, please email me or come in to see me in person. I would love to help you out. All right, good luck, everyone. Bye.